In this video, we're going to think about limiting reactants. And so we're going to build on the skills from the using chemical reactions video. And we're going to think about, instead of just knowing what one reagent compound is, we're going to think about what more than one reagent compound is, how much there are, and what is the relationship between those. So the first thing is, what is a limiting reactant? So we know that a balanced chemical equation tells us this relationship of compounds on the left to compounds on the right. So let's look at an example. So in the pantry, there are 4 pizza crusts, 10 cups of cheese, that's in the fridge, and 10 ounces of pizza sauce. How many pizzas can I make if a pizza is combined of 1 crust, 2 cups of cheese, and 5 ounces of sauce? So the question becomes, how do we figure that out? So we know, based on each of these items, that for the 4 crusts, if we create a relationship of 1 crust to 1 pizza, you can make 4 pizzas. Well, let's think about cheese. So for 10 cups of cheese, we're going to divide that by 2 cups for 1 pizza, and that gives you 5 pizzas. So let's look at the sauce. So for 15 ounces of sauce, it takes 5 ounces for 1 pizza, and that's going to give you 3 pizzas. So it turns out that the answer to the first question, how many pizzas can you make, is 3. And it's 3 because you're going to run out of sauce first. So a limiting reactant is the thing that gets consumed the fastest. In this case, it is going to be the sauce. So at the end of the day, we might want to ask ourselves, how much of each reagent is left? If we can make 3 pizzas, so for the crusts, we're going to consider how converting back from sauce. So for 15 ounces of sauce, there are 5 ounces of sauce for 1 crust, which means that we used 3 crusts. And I am going to move this up so that we can continue to work here, and then we will move that question to the bottom. So for the crusts, there were 4 crusts, and we used 3, so there's 1 crust left. And so in this case, we converted the sauce, which is our limiting reactant, to the other reagents to determine the excess. So for the cheese, there are 15 ounces of sauce. We're going to convert that to cheese. So for 5 ounces, there are 2 cups. In this case, we're going to see that we used 6 cups. And so the leftover is 10 minus 6, which gives you 4 cups. So now we have determined our yield, and we'll go through these definitions in the next segment, of 3 pizzas, and what's left over is 1 pizza crust and 4 cups of cheese. So the next thing we want to think about is, what is the percent yield? And so buried in here or on your slides, you can see it says, if 2 pizzas are burnt and only 1 pizza was good, what is the percent yield? In this case, you could have made 3 pizzas, but there is only 1 product. So the yield is the actual divided by the theoretical. So it'll be 1 divided by 3, multiplied by 100. So that gives you 33%. So you got only 1/3 of what you expected to get. And we're going to look at these terms in detail on the next segment. So let's think about the different terms so that as we move forward in these examples, we all know what we're thinking about. So limiting reactant, this is the reagent that is consumed first. There is nothing left. So a limiting reactant is fully consumed. There is none left. So an excess reagent, there is extra left. So this is determined or calculated by the starting minus used, and that equals the excess. So in this case, if we have two reagents, so if we're going to go from A plus B, and that's just going to create C. The limiting reactant would be either A or B, and it will be consumed first. We can use the limiting reactant to determine how much of the excess reagent is required. And then the excess is the starting amount minus the used amount. So the theoretical yield is the amount of product you should collect based on limiting reactant. So if the limiting reactant is fully consumed, meaning all used up, then all of the limiting reactant has turned into product, and that is the theoretical yield. So that would be how much C you would expect based on what you started with. So the actual yield is the data collected in the lab, or given in a problem. So this is data. You can't calculate the actual yield. Now, in an experiment, you would have to measure or weigh out your sample. And so the actual yield is what you actually collected. And so this allows us to calculate the percent yield, which is the actual divided by the theoretical multiplied by 100. And so this shows how well the reaction went. And so you can get a percent yield of 0%, where you should have collected something and didn't, or you can get a percent yield over 100%, and that likely means that something is off either in your measurements or your calculation. But moving forward, these are the definitions that we're going to think about in the next example problems. So in this example, a scientist mixes together 42.5 grams of magnesium and 33.8 grams of O2 to create magnesium oxide. What is the limiting reactant? What is the theoretical yield? And if 55.9 grams of magnesium oxide is collected, what is the percent yield? So there are three questions: 1, 2, and 3. So in this case, we are going to think about those three questions independently. So let's start with identifying the limiting reactant. So I'm going to move this up a little bit. So the way that we're going to think about this is to go from reactant to reactant. So we are going to convert magnesium to oxygen to ask how much we need, or oxygen to magnesium. So we're going to take our 42.5 grams of magnesium. We're going to convert that to O2. So the molar mass of magnesium is 24.31 grams in 1 mole of magnesium. And there are 2 moles of magnesium for every 1 mole of O2. And in 1 mole of O2, there are 32 grams. And so we need 27.97 grams of O2. So this says, in order for all of this magnesium to be used, we have to have this much O2. That makes it a perfect relationship. So we know that we have more oxygen than required. So we could have also started with O2. So I will show you that calculation of 33.8 grams of O2 divided by 32.00 grams in 1 mole of O2. 1 mole of O2 is 2 moles of magnesium, and magnesium is 24.31 grams in 1 mole. And so that requires 51.35 grams of magnesium. So in this calculation, I am showing you one way. Alternatively, you could have converted both reagents to product, and the limiting reactant is the one that makes the least amount of product. However, on the next slide, on a more difficult exam or an exam-based question, you'll see that this way gets you to different answers. So the answer to question 1 is magnesium is the limiting reactant. So once we identify the limiting reactant, we can actually go ahead and start to answer number 2. What is the theoretical yield? So I'm going to shrink this, give me a little bit more space. So for number 2, we are going to convert the limiting reactant, so the 42.5 grams of magnesium, we're going to convert that into magnesium oxide. So there are 24.31 grams in 1 mole. And there are 2 moles of magnesium for every 2 moles of magnesium oxide. And in 1 mole of magnesium oxide, that weighs 40.31 grams of magnesium oxide. So we can plug this into our calculator and we can expect 70.5 grams of magnesium oxide. So this is the answer to question 2. So now we know how much we should have collected. And so the last part of this question asks, if 55.9 grams of magnesium oxide is collected, what is the percent yield? And so the yield is the actual divided by the theoretical. So I'm going to make it smaller and slide it up again. So the actual is 55.9 grams. We're going to divide that by what we should have collected, which is 70.5 grams. We're going to multiply that by 100, and that gives you 79.3% yield. And this is the answer to number 3. So I'm going to make this smaller so we can look over all of this again together. So there are 2 ways that you could have done the first part. You could have converted both magnesium and oxygen into magnesium oxide. And that would have easily allowed you to answer part 2 and part 3 because you wouldn't have had to take another step. However, on the next example, it's going to ask how much of each reagent is left. And that is impossible to determine without this first step. So in this example, a mining company converts iron ore, which is Fe2O3, to iron with carbon monoxide. They react 167 grams of Fe2O3 and 85.8 grams of CO. With 72.3 grams of iron is collected. And so we want to fill out the following table. So this table has 5 different lines. So it asks first, how many grams of Fe2O3 remain? How many grams of carbon monoxide remain? What is the limiting reactant? So these first 3 lines all are part 1 of the previous calculation. Then it asks what is the theoretical yield of iron in grams. And then it asks what is the percent yield of iron. So in order to figure this out, we're going to need to determine what is the limiting reactant. And to give ourselves some more space, I'm going to slide this information to the left to give us the space to work. So we're going to take our 167 grams of Fe2O3, and I'm going to convert that into carbon monoxide. So there are 159.70 grams and 1 mole of Fe2O3. The balanced chemical reaction is 1 mole of Fe2O3 for every 3 moles of carbon monoxide, and 1 mole of carbon monoxide is equal to 28.01 grams. And when you plug this into your calculator, you get 87.8 grams of carbon monoxide. So in order to use all of this up, this is the number that you would look for. So if you look back in the problem, there are 85.8 grams of carbon monoxide available, which means we don't have this amount. So therefore, iron oxide cannot be the limiting reactant. So let's look at carbon monoxide. So we're going to take our 85.8 grams of carbon monoxide, which is 28.01 grams in 1 mole. And there's 3 moles of CO for every 1 mole of Fe2O3. And Fe2O3 weighs 159.70 grams in 1 mole. And this gives you 163 grams. So if we have 167 grams of Fe2O3, and we need 163 grams of Fe2O3 to use up all of the carbon monoxide, this is our limiting reactant. So now let's go look back at our table. So the limiting reactant is CO, or carbon monoxide. So the second question is, how many grams of carbon monoxide remain? So we're going to take our 85.8 grams. We're going to subtract the amount that we used, which is 85.8 grams, and that should be 0. So the limiting reactant, there is none left. Now, the excess reagent, which is the Fe2O3, we start with 167, and we used 163, and that gives you 4 grams of Fe2O3 remain. So we were able to determine that looking at these equations over here, where what we did is this side is what we have, and this on the other side is what we need. So what we have is what we started with. What we need is how much we need to use this all up. If you think back to the ice cream sandwiches example in a previous video, if you start with 20 cookies to make an ice cream sandwich, if we have 2 cookies plus 1 scoop, that equals 1 sandwich. So in this case, if you have 20 cookies, we need 10 scoops, because that's how you can make 10 sandwiches. So this is the same analogy, just with chemicals. So now that we've figured that information out, our table asks us to determine the theoretical yield. Oh, wow. So that was like a lot of movement. So we're going to take our 85.8 grams of carbon monoxide. We're going to convert that into iron. So there's 28.01 grams in 1 mole of carbon monoxide. There are 3 moles of CO for every 2 moles of Fe, and the molar mass of iron is 55.85 grams in 1 mole. And so this gives us 114 grams of iron is our expected yield. So we can write this in our table, 114 grams. And so if we look back at the problem, it says 72.3 grams of Fe is our actual yield divided by our expected of 114 grams multiplied by 100, and that's going to give us 63.4% yield. Now I'm going to zoom this out a little bit. I'm sorry, the font gets small. So in this case, this is a good example of the best way to think about limiting reactants. So how many grams of each reagent are left over? We can do that by calculating what we have to what we need. Then we can subtract what we have minus what we used. For the limiting reactant, the remainder is always 0. Once we identify the limiting reactant, we can easily determine the theoretical yield. And then we can determine the percent yield. So now let's look at another example. So in this case, a scientist is trying to make silver chloride from silver nitrate and magnesium chloride. The scientist mixes together 12.34 grams of magnesium chloride into a silver nitrate solution. They are able to collect 20.15 grams of silver chloride. What is the percent yield of this reaction? Assume that the magnesium chloride is the limiting reactant. So this example is really just thinking about percent yield, and it's really building all the things we've been talking about. We're going to take an amount and convert that to grams in another component. So let's convert magnesium chloride, grams of magnesium chloride, and we're going to convert that into silver chloride. So magnesium chloride weighs 95.21 grams for 1 mole of MgCl2. There are 1 mole of MgCl2 for 2 moles of AgCl. There are 143.22 grams in 1 mole of silver chloride. And so when we plug this into our calculator, we get a theoretical yield of 37.15 grams. So if this is our theoretical yield, we're looking for the percent yield. So the percent yield is 20.15 grams divided by the 37.15 grams that we actually collected. We're going to multiply that by 100 and get 54.24% yield. So limiting reactants are the reagent that is consumed first. We can then calculate how much we should have gotten, what our yield is, and everything else.